Welcome to the video tutorial for analyzing graphs. In this video, I'll explain how to find intervals of increase and decrease, and I'll also briefly show some examples of domain and range. Let's start with a quick review of some inequality notation. I found that a lot of people struggle with intervals of increase and decrease, not because they can't really see them correctly, but because they're not sure how to write down what they see. My recommendation is to always translate what you see into words before you write the inequality. For example, look at these three simple number lines. If I wanted to describe in words the first number line, I might say that the graph is shaded after 2. That word after becomes your signal for which inequality you should use. X always goes in the front of your answer. And the inequality symbol for after is going to be a greater than symbol. Couple ways to remember that. First would be to think of the inequality as an arrow, and the arrow is pointing the direction of the shading. Or another way to think about it is the numbers in this shaded portion of a normal number line. These are numbers like 3 and 4 and 5, and those numbers are all greater than 2. X is greater than 2 is the appropriate inequality for this graph. By the same logic, if I wanted to describe the second graph, I would probably say that the shading is before 2. Since I can't see where it ends, I have to assume that it continues on forever. So I'm not going to try and name a number on this side. I'll just use 2 as my marking point. To translate before 2 into an inequality symbol, we will use the less than symbol. Just like above, there's two ways to think about it. You can think about the arrow pointing the direction of the shading left, or you can think about what numbers would belong on this side of 2 on a normal number line. It would be 1 and 0 and negatives. Those are all less than 2. So what can we make of this last number line? Well, if I just describe this in words to a non-mathematician, it would seem pretty logical to call this in between 0 and 4. The shading is between 0 and 4. That word between is your clue that the inequality for this type of graph has two inequality symbols, and X is in between each of them. You are always going to use less than symbols, and you're always going to put the smaller number first and the bigger number last. Both of the inequalities point to the smaller number. They also both point to the less than side of a normal graph. Notice how the inequality matches the graph. First comes 0, then the shading is represented by X, and finally 4 is where it ends. Okay, armed with these skills, let's turn to an actual graph in 2 dimensions. Now, in this example, obviously we're looking at the graph of a function, and it's got an x and a y-axis. But the same logic we used above will apply, because when we write the intervals of increase and decrease, we really are only interested in charting the x-axis. So for what I'm about to do, we'll ignore the numbers on the y-axis. To find the interval of increase, I'll start by looking at where the graph is going up. Remember that you read from left to right. So for example, if I start here at this end and I start tracing the function line, I notice that the line is increasing, 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 all the way up to this point. It would be natural maybe at this point to worry about what's going to happen. And luckily, you know that this is called an asymptote, and it means that the graph instantaneously switches from continuing up in this direction to picking up down here. Just because it jumps down doesn't mean the function decreases. That jump happens in an instant, just like by magic. As we pick up perfectly here, when you actually do continue up the line, it turns out the line is still increasing, despite that jump. In fact, it continues increasing all the way to this point right here, which you may recognize to be the vertex. After that point, the graph is now going down. And even though it jumps over the asymptote, when I get to the other side, it is also still going down. So I've now highlighted all the parts of the graph that are increasing. My next goal is to be able to write an inequality that represents the parts that I've highlighted. If we go back to a moment to our non-mathematician friend, describing this graph just using normal words, it would be pretty reasonable to say, well, the shaded parts of the curved line are all on the left-hand side of the graph. In other words, they're all before this red point right here. Well, since we are mathematicians, we can be a little more specific than that. We could say that the parts of the graph before that point, and specifically that point is the point -1, 1.2, well, the parts before that point, those are the increasing parts of the graph. To translate that into an inequality, we're going to focus only on the x-axis, which means we're really only going to need the x-coordinate of the point, and before means I should use a less than symbol. This graph is increasing when x is less than -1. In other words, if you looked at the yellow portions of the graph and you squeezed them down into one dimension, you would probably end up with a number line that had the yellow highlighting only on that part of the x-axis. That's exactly the inequality that we've just written. To write the interval of decrease, we follow the same process, only now we're going to look at the non-highlighted parts of the graph. If we describe it just using normal words, we would probably say this graph is decreasing after the vertex point. In other words, the parts of this graph where x is greater than -1 are all decreasing. Take a moment to make sure you've got that. And now we'll switch to talking about domain and range. Domain and range are also related to the graph and the x and the y-axis. However, they are a separate skill. To understand what the domain is, remember that domain represents a list. It's a list of all of the x values that are part of this function's curve. For example, -6 is in the domain because I can find a point right here that has a -6 x-coordinate. Now that point also has a y-coordinate, 2, and 2 would be part of the range. Because there are infinite points on this curve, for example, this one here with an x value of -2, and this one with an x value of -4, it would be kind of silly to list out all of the x values of all of these points. So instead of making a list that's really long, in fact infinite, we're going to use a shortcut. And the shortcut is this symbol. It looks like an R with 2 bars, and it means all real numbers. Almost every number is in the domain. And I say almost because there are 2 numbers that are not. You should start to recognize what they are based on your understanding of rational functions. And the 2 numbers are the 2 numbers of the asymptotes of this function. More specifically, the vertical asymptotes. Vertical asymptotes are dotted invisible lines that never touch the function. In other words, this dotted line right here, the line that goes through x equals -3, this dotted line never touches my graph, which means that there's never going to be a point that's on my graph that has an x value of -3, which means that x equals -3 is not in the domain. So we say the domain is all real numbers except -3. And similarly, there's never going to be a point with 1 as an x value, so we also accept +1. Notice that the numbers that I'm writing here match the graph. I'm describing what I see. I'm not flipping any numbers. For range, we do the same thing, but for the y-axis. So let's start to look at some y values that are in the range. 4 is definitely in the range. I can see points here and here with a 4 for a y value. 6 is definitely in the range. So is 0 and -2. To make range a little easier on myself, I'm going to try highlighting the y-axis in all the regions that have points with those y values. When I do that, I can easily see that all of these numbers have points with those y values. I have to stop at 2 though, because you can see what happens at 2. There's a horizontal asymptote, which means that as far as I go to the right or the left, there's never going to be a point exactly on 2, which means 2 is not in the range. Now, you might be tempted to say the range is all real numbers except 2 and move on. Be a little careful though. Down here on the bottom, it's easy to see all these numbers are in the range, but you should be a little doubtful about this little middle section. If we said that the vertex was at 1.2, that should be the highest point, which means there's a tiny little gap right here. There's a little gap, and all the numbers in this gap are not in the range, because no matter how far I go on either side, I can't see a place where my function crosses into this region. So we're also going to start with all real numbers except, but instead of just listing one or two numbers, we're going to list all of the numbers in here, which actually means we need to write an inequality because there's infinite decimal points right in there. That inequality represents all the numbers that are between 1.2 and 2. And you probably heard the emphasis on between because that signals that the inequality is going to look like this. All real numbers are in the range except the numbers between 1.2 and 2.